Dzień dobry. Okay, that's all the Polish I have, I'm sorry. But I'm working on it, I am. So thank you for having me, and thank you for the introduction. My name is James Kretchmar, and I am the CTO for Europe, Middle East, and Africa at Akamai Technologies. Now, I hope you know already who Akamai is. If you don't, you're about to learn maybe one of the really cool secrets on the internet. It might be the coolest company you never heard of. If you do know Akamai already, I'm going to pull back the covers for you a little bit, to pull back the curtain, so you can see a little bit about how it works and how we do what we do. Now, in particular, I'm going to talk about how we scale to serve the largest events on the internet, big events. And you think, okay, what's a big event? Is he exaggerating? What do we mean by large? Well, here's what I mean by large event. Things like the Sochi Olympics, the Winter Olympics earlier this year. This is a very large event. It was delivered to a global audience, a lot of high-definition streaming video. We can look at a little bit of an overview. There were many rights holders here, 25 different rights holders that were broadcasting this content. NBC, TV2 Norway, French televisions. The coverage, 24/7, over the course of 17 days, live streaming of all 98 events to a truly global audience and users all over the world. And it used a variety of media technologies, different streaming formats, streaming protection, and other technologies. But in terms of size, because what we're going to talk today is about scale, these were some of the bit rates that we delivered at peak. You can see the largest was a hockey game between the United States and Canada, which peaked at 3.5 terabits per second for an online streaming event. This is big. You know, we think to 10 years ago, there was not a lot of streaming media on the internet. There was a little, but this is getting to be serious amounts of data. If we look at it another way, how big we had to scale for this, here's the number of viewers. So over 2 million simultaneous online viewers of this video content. So imagine this, right? Imagine if someone said tomorrow you have to go out and support an event that's going to have 2 million simultaneous viewers of high-definition video, and a lot of them have paid for it, and so they expect it to work and not have any glitches or problems. That's really hard to scale for, right? It takes a lot of special stuff to do it. All right, so this was a big event, the Olympics. There was a bigger one this year. Any guesses? Yeah, football, soccer, because I'm American. I'm based here in Europe, but this was enormous, right? So for this, Akamai worked with FIFA to deliver this content through many partners that they had in order to deliver it into various countries around the world. So we're talking about 80 countries, over 50 rights holders. A summary here, you know about the sports part, but in particular, it used all of the streaming technologies. In terms of traffic, we were talking 6.9 terabits per second at peak. That's just for this event part of the traffic. Remember that Akamai has all this other traffic on the platform, about 10 terabits a second and more over time. But this was just the event that had to support 6.9 terabits per second. Unfortunately, we can't give out the number of simultaneous users, but we can give, for example, that just for the Belgium-United States game, just from the USA, there were 5.3 million simultaneous users. And you know, football is not that popular in the US. It's climbing in popularity, but to have 5.3 million users in the US alone is very substantial. And there's a final statistic here which mentions that one of the rights holders measured that the average viewer experience, they watched the game for 47 minutes. So this is not, I'm going to the internet to watch a funny clip my friend sent me. This is a long viewing experience, high definition, lots of data. Needs to scale. One other thing to note about this traffic for the FIFA World Cup is that it was not a kind of smooth, steady growing, you can watch it 6.9 terabits per second. This was very spiky traffic, right? This is traffic which shows up all at once right at the beginning of the match, and then it lasts, and then it's gone. And I think you know, in provisioning for the types of things you do every day, that's very hard to manage. You don't know exactly how it's going to look before it shows up. You have to account for things that are going to go wrong before you see them. This is tough load to deal with. So that's an additional challenge to scaling, not just the raw size, but the way in which it might come at you by surprise. So one other thing I'll say about the events, these huge events on the internet, is that they're getting much larger over time. This is a graphic showing the differences between the FIFA World Cup in 2010, and then the 2012 Olympics, and then 2014 Olympics, and 2014 World Cup. And you can see the spikes here are getting much, much larger over time, even just in a span of 4 years. A slightly clearer way to see it, this is sort of the relative event size. If the World Cup in 2010 was size 1, okay. The World Cup this year was 8.4 times as large, right? This is just the span of 4 years. So if you imagine all of the graphs that you see about the explosion in internet traffic, right, and how it looks like an exponential curve, it's true, number one. We're right in it. I know that from day to day, it's sort of hard to see that because we're on this little ant on the curve that's climbing along, and it just gets a little bit bigger each day. But over 4 years, 8 times as big an event. And we know that's going to get even larger in the future. World Cup 4 years from now, it's going to be enormous in terms of internet traffic. So these are the huge events. These are the large events on the internet. So let me talk a little bit about Akamai in general first and how we come to play here. So Akamai has this very large distributed platform. It's 149,000 servers located in 92 different countries around the world. We're delivering over 2 trillion internet transactions every day. And in the end, this ends up making up about 30% of the traffic on the web. So a lot, right? 30% of the traffic is a lot to deal with and a lot to manage. On the platform, we really have a wide variety of different types of customers. Most of the leading sites for e-commerce, for media, of course, which these events are, but also for finance, large sites for example, antivirus protection. So we're in an advantaged place here. We get to see a lot of what happens on the internet. But let's talk about how to scale it now. So I'm calling this Scaling 101. We're going to go through a bunch of phases of what needs to be done to serve these enormous events. 101 in American universities, that's usually the introductory level class. So, okay, you're starting out in a subject. What's the first thing? So first, we'll talk about highly distributed, what it means and why it's important. Okay? So let's go by way of example, starting with a centralized deployment. Right? So this is, okay, I'm going to deliver an event on the internet, and maybe I want to try to do it all from one great big data center, located somewhere with good connectivity, somewhere close to a lot of end users. All right, well, you can try to do this, but it's got some problems associated with it. One thing is that origin, that data center with the content, is going to have to handle all of the traffic coming from all of the end users in that one central place. So it better have a tremendous amount of capacity available in terms of servers and network bandwidth in and out of the data center. But there's things to think about there, right? Even if you have in that data center 3, 4, 5 connections to the internet, you'll be constrained in that area because just a few hops out, everything is going to get converged. You won't find enough free paths because all the data is trying to concentrate in one place. So that's a big problem if you were going from a central deployment. At the same time, you'll notice that the average distance between an end user and the servers is very high, right? You may be going thousands of miles away, and that means lots of opportunities for packets to get dropped and connection problems. It's going to be a slow, bad experience. But I think this is not a surprise to anyone. We're all living in a world now where we know one centralized deployment for a major event is probably not a good idea, right? So we'll go to the next obvious thing, right? A moderately distributed deployment. So what do I mean by moderately distributed? This might be, let's serve the content out of 10, 20, maybe 30 different places around the world. And that sounds pretty good, right? 30 different places, you're close to a lot of people, right? You're on several different continents. It's certainly a better story than centralized. The question is it good enough? So, okay, in this scenario, you start to get some offload of the origin because people can share a little, though a bunch of people will go to one data center and then only that has to go back to the origin. So that can help. You might be in better shape in terms of the origin not getting overloaded. But you still have the difficulty that each of these, say, 20 data centers, they're still going to see a lot of load, right? If we talk about the 2 million users, right, that are watching simultaneously, then you haven't divided it up that much. You're still going to have a lot of load in each data center, and you're still fairly far away from the end users. End users to data center might be in the high hundreds or 1,000 miles still. So not the best picture. This is where Akamai is. Highly distributed, deeply deployed. Now, actually, in order to make the picture make any sense, in the previous versions, I just showed sort of one computer to represent an end user, but it only makes sense here if you show a reality, which is lots and lots and lots of end users, right? And when they connect in this environment, it looks more like this, right? Now, you get tremendous offload from the origin, right? And I recognize there's differences in live and VOD here. We can talk about that. But you get fan out here so that the origin doesn't have to get so much bandwidth and so much load and so much connectivity to it. And at the same time, the end users are very close to the servers, which means less opportunity for problems, higher bandwidth streaming. If you're familiar with the bandwidth delay product, you know TCP is only going to let you go so fast if you have a long latency between yourself and the server. So this helps with that. This drives high definition experiences. So this is what it looks like to be highly distributed. But to put it in perspective, where those three sit in terms of each other, on the far left of this chart is showing a centralized deployment, number of deployments 1. And you can see the average distance to end users is very high. Some will be on the other side of the planet. If you move to somewhat distributed, just the 30 data centers, look how little that moves you, right? It helps bring down that average distance, but you're still talking maybe 1,000 miles or more, right? It's not until you get up to something like 2,000 deployments around the world, where an Akamai is, that you can really bring that latency down to something like 250 miles. And when you're at 250 miles, it's a substantially different story. That's high definition, stable experience. Okay? So that's sort of the first part, is having this highly distributed network. But there's one other thing that's important about being distributed that's actually not about the geography or the fan out, right? And that's to do with the way routing on the internet works. Now, as you know, the internet is made up really of a combination of many, many networks that are all interconnected. So on the left here, we have a bunch of servers that are going to serve some content. On the right, we have end users who would like to visit that content. And in the middle are all these many, many networks that are the internet. And in particular, there's connections between the networks. Right? These are one network's connection to another to pass the data off. Now, these are important because they're often the slowest part of the internet. They're most congested. There's not a lot of extra bandwidth available. At peak usage times, there's packet loss and congestion. Right? But in order to get my content from a server, I have to cross these networks. Right? I'm at home on my ISP. The content's on some other ISP. So you travel through network to network to network through these bad peering points and then don't get good quality service. If you're highly distributed, it means not just being in many locations and many geographies. It means being in as many end-user networks as possible. Because if the server is in the same network as the user, it'll be very good performance. My ISP, I'm at home with my computer, and I visit a server that has the content on the same ISP. I don't cross any peering points, and it's just this green line here, much, much better performance. So this is really where Akamai started, was avoiding the congested peering points on the internet. Okay, so this is all scaling 101. Let's go to scaling 201. And this is about intelligent algorithms and fine-grained load balancing. So we'll go back to our highly distributed deployment picture here. But we have some challenges with this highly distributed deployment. In particular, we want to serve end users from a server that's close. That was the whole idea, right? If I have servers everywhere, but I send a user in Poland to a server in Australia, I haven't done a good job. So I have to do that. I have to figure out which server is best. I need to fully utilize the servers, right? Because if I can't fully utilize them, I either need to pay for many, many extra servers, right? Or not have enough money to do that and run out of capacity. So this is critical. How do we get to fully utilize each server? I need to predict and prevent overload, right? If it doesn't matter if you have capacity available in one place and not another, and end users get this event served at bad, bad quality. That's not scaling, right? So the typical approach for a CDN here is called IP Anycast. Let me get a quick show of hands. How many people in the room know what IP Anycast is? Okay, good. I like coming to technical events. This is great. Okay, so the short version, if you're not familiar with it, BGP, the way it usually works, you have your address space that you want the rest of the world to reach, and so you announce it from your data center through a BGP announcement, and the rest of the internet learns how to come to your IP space. The IP Anycast trick is you say, all right, I want to sort of get users as close as possible to some data center. So you take one IP address, or a range of IP addresses, a /24, and you announce it from all of your data centers, right? Now this way, BGP is learning all of these different ways to get to this one IP address. And BGP is designed to try and find something like the shortest path to that data center for a given end user. So this is one strategy you can take. There's CDNs that do this, that will publish one IP address for the event or the content, and then let IP Anycast get the end user to something nearby. But there's some troubles with Anycast. First one is it doesn't actually find the best performance. Right? There's a variety of ways to measure real performance. If we're talking about a video event, this could be the number of rebuffers. This could be the bit rate. Do I get true high definition, or do I get grainy, low bit quality? You can look at loss. You can look at latency. But IP Anycast doesn't look at any of that, really. Right? It doesn't account for congestion in any way. So if you have a very overloaded pipe, it doesn't help. It'll send users over that overloaded pipe just because it looks like there's one hop less. It's also very coarse, right? It's not fine-grained. Anycast just kind of takes large groups of end users and gets them vaguely towards some servers, right? So you don't have a lot of control there. It also won't work for this reason for very highly distributed environments, right? You have very fine-grained servers placed all around the world, but Anycast is a very rough tool to get the traffic there. You might actually not even be able to utilize some of your servers. And finally, you have very little control with Anycast, right? If you decide you want to send traffic somewhere else, you barely can do something about it. There's path prepending and other techniques, but it's very, very rough. So we need a system with fine-grained control here, right? We want to be able to say, I need to send these users right now to these machines. So how can we do better than Anycast? Well, there's a number of techniques, but one of the major techniques we use at Akamai is through a DNS-based load balancing. So we'll take the host name that we want to deliver the content on. Here it's example.com. We'll CNAME that over. First, there's a couple of administrative static CNAMEs just to keep track of things. But the real magic happens in that a1782.g.akamai.net host name. Because that goes into the special Akamai DNS servers that are dynamically figuring out where we want to send end users and returning those answers based on that question that got asked. So this is very powerful now. The parameters there may change, the 1782, the G, the name, they'll change a little. But the key thing is we're updating those answers all the time, and it's based on the person who asked. So we send someone coming for content to exactly the best server for them. So this is good. Now we have something in our tool belt, right? We can choose exactly which server we want to send the end users to. What does that give us? Well, first of all, this lets us drive server utilization up to close to 100%, right? Because now we don't have to worry about traffic that's out of our control. We can let the traffic grow, measure exactly how utilized that server is, and then stop sending end users there. Or if we find we're getting hotter than we would like to run, we can send them somewhere else. So we get very efficient utilization of our servers. We don't have to deploy excess capacity for this reason. We can also deal with enormous traffic spikes, right? Like look at that spiky traffic for the Olympics. Why? Because we can take the traffic and decide, okay, this needs to go there, this needs to go there, absorb all of it, send it somewhere reasonable, right? If you have Anycast, you just get overwhelmed and have not a lot of ability to balance around. It also lets us send end users to the best performing server. Now, we have to figure out which one that is. That's going to be its own challenge coming up. But at least we've got the tool to do it now, right? And one other piece, this also gives us the ability to find and route around problems on the internet. right? If we detect that a network cable has been broken or there's congestion or packet loss or some catastrophic event, we can find another path for those end users, intentionally sending them to a different server. BGP doesn't always find this. I think you heard in a talk this morning, BGP has problems with this sometimes, right? But we can work around that. So, the intelligent algorithms piece. So now we've got a lot of control, right? And control is good, but only if you know what to do with it, right? So this is like we started with a very old car that couldn't do anything. Well, now we've got a Ferrari. We've got a really good machine, right? But the machine is only as good as the driver. So how do we use this? Well, first of all, we need to understand the structure of the internet, right? So that we know what we have to work with in terms of what traffic is going where. We need to measure the performance between servers and the end users that are going to visit them in real time. So we want to know right now, not just how many AS hops am I away from some content, right? I want to say, this group of end users, here's the set of servers and deployments that we most likely want to serve them from. What's the latency and loss to each one? How does it look? What are the internet conditions right now? And let's choose the server based on that so that the end user gets actual, real, best service. So we'll assign to the best performing server. Of course, if that server is going to become overloaded, then we have a strategy for fairly choosing the next server and spreading out the load. Now, load is a very interesting question in a scenario like this, right? Because you make a decision when someone makes the request, right? They look up that host name, and you're going to hand out an Akamai server. But you don't really know, if you're starting from scratch, how much load is going to show up. Load is a tricky thing. The load that shows up, it might be heavy, it might be light, and it might be heavy on a number of different resources, right? It could be CPU-intensive traffic that shows up, or it could be intensive use of the bandwidth in and out of the server, or it could heavily use disk I/O operations. You really don't know. So there's some sophistication that's needed there to estimate the heaviness of a request when it comes in, and then to measure it on the different resources and adaptively learn over time and have a load feedback loop. Okay? So this is pretty good so far. We've got a pretty good system now, highly distributed, and we know how to control it so that we can get the load to the places we want. So this is actually very sophisticated, and I shouldn't say that these are the basics, because this is the most sophisticated system for this in the world. But I'm going to go one step further with scaling 301. And this, I think, I'm going to say is a little bit zen. I'm going to say something, I hope, maybe a little profound, maybe not. But that reliability and scalability are in many ways the same thing, right? We think of them as different. Scalability is how do I make it big? Reliability is how do I make it work all the time? But the truth is, I can achieve scalability if I work really hard at reliability. And if I don't work at reliability, I'm not going to get scalability. So what do I mean? Well, we know that there's a certain cost associated with redundancy, and that we need to have some redundancy because stuff breaks and goes wrong, and we can't have the service fail. So anything that can break needs to have some kind of backup. Okay, this is natural. Now, a backup means some extra resources are needed in the system, right? We'll need another of that thing, but that also means extra cost. But the critical thing is to remember that if there's small failures that can cause bigger pieces to fail, then this is going to be a losing battle, right? If you imagine that I've got a big cache at a particular data center, and I say, okay, well, I need it to be redundant, so I'll have a second cache in that data center. And then if one fails, I've got the other. But what's going to trigger one cache to fail, right? If that can happen easily, and then you've lost half of what you were thinking of as either spare capacity or completely backup, you're not in a good situation, right? So in order to really effectively use large capacity, you have to minimize the impact of small failures. Now, the easiest way to describe that is an example we all know, which is RAID for disks, right? So I can make effective use of very large amounts of disk space if I have, say, 5 active and then 2 that are acting as parity disks. Any 2 disks can fail, and I'm still okay. I haven't lost a lot of capacity, so I've made it out of redundant, reusable parts. That's much more efficient than having 2 completely separate disks, and one goes offline, and then I'm in trouble. So Akamai treats reliability in much the same way. right? We build reliability in layer upon layer upon layer. Every component, every piece of software has its own way of looking at what do I need to do to function all of the time and to deal with problematic scenarios. So what happens is each of these deployments, these Akamai deployments, they look like one big cache, right? I've drawn them here as a server, like a big server. But let's zoom in now and see what makes up one of these deployments, because this is where it gets interesting, right? Each of those deployments is really a rack or a part of a rack or many racks, but it's made up of a collection of individual, more or less off-the-shelf servers. It's commodity hardware. It's not very, very special. And you'll see that we treat each of these servers in a way so that if one fails, the system keeps going and adapts to it, and it's not a problem. We've isolated the small failure from affecting the entire system. So for an example, within a deployment of servers, the disk space is effectively shared. Right? They're not all connecting out to one big disk service that might fail, or even two. We use the disk on the machines, and all the machines have algorithms to talk to each other to treat it like a big shared cache space. Customers are striped across the different servers. In fact, the number of servers that a piece of content is served from is going to become dependent on its load. So we can start with content on 2 machines, and then say, the load on this content is becoming higher. It's in high demand. It's very popular right now. We need more machines to serve it. That mapping system that hands out the DNS answers will start to add machines to that set. So content dynamically on different machines. Now, where it gets really interesting is if a server fails, right? So the first thing is, and this was one of the algorithms on which the company was founded. You can find the research paper online. There's a hash mechanism that gets the content onto different servers in the region. If a server fails, we want to reassign that content to other machines, but we don't want to use a hash that would scramble all the content onto new machines. So you have to find a special type of hash algorithm that was research that came out of our founder from MIT, and it's called consistent hashing. It's fun to look at. But we'll find a new home for that content. DNS will then reflect the new assignments. But in the spirit of layer upon layer upon layer of redundancy, we don't like that there's 20 seconds where the DNS TTL has not expired and a user could be sent to that IP address. So one of the other machines in the rack, they're all running a number of distributed algorithms. It will notice that one of the machines failed, and it will take over its IP address and provide service on that IP address. It's very fast. There's many other layers of redundancy involved that I haven't talked about, but maybe a future talk. So the deployment, it acts like one big cache, right? But you can have multiple failures of these independent machines, and it continues to function with no bad effect. So this really lets us be reliable, but also lets us scale, right? We can have a machine down for maintenance, another one fails, and another one's being installed, and it's all fine. Okay. I'll take a very quick look, just a brief tour of what the future is going to be, because scaling to the future is going to bring new challenges. So all of these charts you've seen like this about the growth of video traffic on the internet that looks like it's going to go crazy, well, they're all true. We look 10 years ago, what we're doing today compared to then, but 10 years from now, it's going to be enormous. One way you can look at it is to say, we know how much we're doing today, but if we look at this enormous World Cup event, but then we compare the amount of online viewership to the total viewership, it's still just a percentage, right? And more of that's going to shift to online. So we've got a lot of growth to deal with, so much that we're going to need new technologies and new techniques. We'll still need everything we have so far, but we'll need more stuff. So to talk quickly about where we see the future going, we think there's going to be a lot more technology required in the client, right? In the player, in the device, in the phone. So we're working on a SDK and some other technologies that can go in the devices to speak new types of protocols. One example is hybrid HTTP UDP. Right? We all started with UDP-based streaming protocols, but those had problems, and now pretty much the whole industry has moved to HTTP-based protocols. There's still a little UDP. And that has a lot of good properties, but we realize we've also lost some of the good properties of UDP. So now we're working with a hybrid protocol that can use HTTP for control and UDP for the transmission of the data part. That brings a lot of good properties. Another one is multicast. I think of multicast now like IPv6 in the sense that it's been around for forever, right? I mean, I don't know, 20 years, 25 years, more. But it's never really taken off, just like IPv6. But then there was this year with IPv6 where all of a sudden, yes, we're doing it. And everyone was on board. It hit a certain tipping point. And I think that will happen with multicast too. We don't know what year it will be. Maybe it will be next year. Maybe it will be 5 years. But we're working now to put the technologies in place to actually make multicast work, to overcome some of the gaps that have made it difficult to adopt. There's also a peer assist. This one's interesting. In many ways, it seems like it's a very promising future, but of course, for ISPs, it could also be a concern or a benefit, so the jury is out. But this could be one of the major areas to help scale the future of online video. Oh, sorry, I was on the wrong slide. This one was for intelligent prepositioning. So there's a lot of cases, not live, of course, but for video on demand, where you could have the content already at the device before the viewer wants to watch it. There's no reason it needs to be all delivered at peak times. Okay, so that's the prepared discussion. I wanted to leave a little bit of time for questions. I think we have a few minutes, yeah? Okay, so I'm happy to take your questions and talk about any of the technology part of Akamai. Or I've put everyone to sleep, is possible.
I know there are a lot of CDN and similar companies on internet. How do you, what can you say about Akamai? How does it stand out? What are the differences, maybe from the technical point of view, if you know, maybe not without sharing some names of other companies and saying bad about them, but what do you think is unique about Akamai?
Yeah, I'd be happy to. And the only thing I want to talk about is technical, because that's my specialty. So I'd say there's two major ways that we stand out from the other players in this field. One is that none of them are doing this high-quality measurement of internet connections in real time, measurement of performance in real time. We're the only ones that are really doing fine-grained, huge, deep deployment, 2,000 locations around the world, 90 different countries. So that's one way that we stand out in a major way. The other one, actually, we never put up on slides because it's something that people don't think about, but it maybe is even more important. There's a lot of things that we've done behind the scenes that we don't sell as a product, but that make the system work all of the time. So there's another player in the field who, I think it was about a year and a half ago, they had an entire outage of their CDN. The whole CDN was offline for an hour and a half, right, because of a bad configuration that got pushed out. So that's bad, that's disruptive. From our point of view, it's unacceptable. So we've built a lot of technologies on the back end, and we did this 10 years ago, to ensure that something like that will never happen. There's automated safety systems for detecting problems on deployment of a new config, halting those and then pulling them back. There's security systems in place that are very advanced to protect from internal and external threats. So that stuff's not visible, but it's the kind of thing where it'll be a problem someday if you don't have them. We made the investment early on, and it keeps us stable. Yeah.
If you have one source like the Brazilian soccer game for the data and you want to distribute it across Europe, how you do it? Okay. That everyone is able to see the soccer game in real time in Europe.
Right. So it's a little bit of a tough question to answer because there's hundreds of technologies involved. If your question is along the lines of how do we not get constrained by fanning it out, right? I mean, that's one piece, is to make sure that end users go to servers that are near them, but then that all gets collected and then goes to a smaller number of servers above that and a smaller number of servers above that. That's one piece. Another piece is this system which needs to make sure that it's really sending the end users to that closest, fastest server, because if that piece isn't there, you have other problems. So really, there's just ranges of technologies and techniques that are involved. But what's clear is that you absolutely have to be very highly deployed, very highly distributed network with a system that can take advantage of and measure that.
Okay, thank you.
Okay. Any other questions? No? Okay. Well, thank you for coming.
Thank you for your lecture.